So I'm very happy to be here back in Santa Cruz, where I lived 2 years around 2000. One of my sons was born here. He's very proud. He's here. And today I will present some results that came out of the team working in the Astrodee consortium. And I will just have one slide of introduction of this European-funded project, which is led by Adriano Fontana in Rome, and with Jim Dunlop, myself, and Sébastien Derrière of CDS Strasbourg, and Sandy and Harry Ferguson in the executive committee. The goals of this project are to dig into confusion within the Herschel, Spitzer, and X-ray images, provide new catalogs combining all the wavelengths together, as well as tools that are delivered and simulated mosaics at all the wavelengths that people can use to test their own tools. And we will also deliver a well-detailed model to generate those catalogs. So I won't enter into the details of the goals of Astrodee that will be presented in the very near future, but I just wanted to warn you that these products will be soon available to everybody, and really the idea is to make that public. And our goal is to study high-Z galaxies, but today, so I have two things, maybe I took the wrong one. No, it doesn't work. Okay. I can change the slides. Okay. Today, what I would like to address is the view from Herschel and ALMA on distant star-forming galaxies, and what is causing the drop of the star formation rate, stellar mass, main sequence with cosmic time. So, in a recently published paper with my PhD student Corentin Schreiber, what we showed is that you can use Herschel to probe the main sequence at up to redshift 3.5. So what you can see in this image, the dots here are showing the detections with Herschel, and as you can see, rapidly above redshift 1.5, you don't see the main sequence with detected galaxies. However, what you can do is stacking, which is a method that has been used by many people, and that's what you can see with the orange line here, that allows you to prolongate the detection of the SFRM star relation down to lower stellar masses and higher redshifts. Now, the problem is that the main sequence idea comes out of the tight correlation that exists between star formation rate and stellar mass, and having a bigger correlation is not necessarily physically meaningful. So what you really want to know is what is the dispersion in the regime where you can only do stacking. And for that, what we discovered is that you can use stacking in another way, which consists in using the median absolute deviation, or in some sense the AMS, of every individual pixel in the images that you're using to stack. And what happens is that if you have only noise or randomly distributed sources, you will have a very good determination of the noise in your image in each one of those pixels. But if instead you have consistently well positioned in the center sources that are making the main sequence in the center of your image, what will happen is that that position here will measure the dispersion of the fluxes of the sources themselves. You can feed that with a PSF, and we've tested that with simulations, those simulations I was mentioning to you based on the Astrodee collaboration, and we were able to show that you can actually measure the dispersion of the fluxes of the sources that you can stack. And that has allowed us to show that 70% of present-day main sequence present-day stars were formed in a main sequence mode. The stacking were done in selecting galaxies, the UVJ diagram for selecting star-forming galaxies and in various stellar mass beams. Now, what you get is a main sequence, as you've seen several times, the Whittaker et al. Paper and others, showing that kind of evolution of the main sequence as a function of time. And I would like to zoom now in this change of slope of the main sequence at high masses. What is causing the drop of star formation, of specific star formation rate at high masses? Is it a lack of gas, or is it something else? At low redshift, there was a proposition by Abramson et al. 2014 that this is just due to the fact that the stellar mass you use in the x-axis combines the disk and the bulge. In practice, there is no reason why adding a bulge on top of a galaxy would make the star formation rate rise. So let's say you have a galaxy which is a pure disk and you add a bulge to it, that will only create dispersion or reduce the increase the mass without increasing the star formation rate. So what they did in this paper for the Sloan galaxy at redshift 0, they deconvolved the bulge on the disk and determined the stellar mass of the disk only, and they found that the slope which was here was flattened when you used only disk masses. Now we thought that this could be an explanation also for what we see at redshift 1 or 1.5 with this drop of the main sequence, so we try to do the same. So we decompose, thanks to the Condell's images in the H-band, galaxies into bulge and disk using Game 2D. We also tested that with GalFit, bulges between having a sourcing index of 4 and disk of 1, a very simple decomposition with a resolution of 500 parsec at redshift 1. And you can see here the quality of the decomposition. We have tested our measured bulge over total ratio with the simulations, because as I said, in the simulations that we have performed in Astrodee, we also include the shapes of the galaxies, and with the mass to light ratio that we've measured for galaxies which are bulge dominated, we were able to determine what is the typical mass to light ratio of a bulge, and that determined, based on the luminosity of the bulge that you decompose here, what is the mass of the stars in the bulge, and subtract that to the total to get the mass of the stars in the disk. And what we see is a comparison here between the bent SFRM star relation when you use all the stellar mass to the one you get when you use the disk only. And as you can see, you don't correct the bending at all. You have a slight correction, but the idea that this is due to bulge only is not true at redshift 1. So what could be the cause? And already an indication of that is shown here, where I don't go into the details, but I just want to show you that when you look only at disk-dominated galaxies, you can clearly see that correcting for the bulge in disk-dominated galaxies make no effect, and disks, pure disks, are also showing this bend. Now, what is the reason of the drop of the SSFR at high masses? And as I will try to show you that maybe galaxies get drunk before they die. So, to do that, what we've done is we used the stacking measurements with Herschel in all the Herschel bands to measure the dust masses in the way that has been described to you by Linda and Reinhard. You have a full fine Fourier DCD from which you get the dust mass. We use the fundamental mass metallicity relation, so using the star formation rate and stellar mass to get the metallicity. For each metallicity, you have the gas to dust ratio from which we derive the gas mass. Then you can derive, you can try to see whether this drop is due to the gas fraction. Is it a drop of gas fraction? And so what you can see here is the gas fraction of galaxies, which does decrease with stellar mass, but in the place where we have this drop, that means in between these two beams, the gas fraction is relatively constant. So the change of specific star formation rate we see here is not due to the gas fraction. So what could be the cause? Now we look at the star formation efficiency of the galaxies as a function of stellar mass, and you see the star formation efficiency rises with stellar mass and then drops at high masses. So the reason for the change of slope of the main sequence at redshift 1 is a real drop of the star formation efficiency of the galaxies. Now if you look at redshift 0, we use the Herschel reference survey, we find that the drop in specific star formation rate that is taking place at redshift 1 around 10 to the 10.5, in practice at redshift 0 is taking place at much lower masses, and if you measure the gas masses again with the Herschel data at redshift 0, you find that the star formation efficiency that was dropping here above 10 to the 10.7 is dropping here about 10 to the 10.2 or 10.3. So you have a decrease of the mass at which the star formation efficiency is dropping in galaxies. So one way to see that is the following. You have a relatively flat specific star formation rate as a function of stellar mass for the blue star-forming galaxies, and here you have a cloud of massive and red dead galaxies, and then you have a break at high masses that is more and more pronounced, going to lower and lower redshifts. So in some sense, it's as if you were dropping wine, while you have the blue wine in the bottle, which is the main sequence, which is becoming red and feeding the red cloud. So do galaxies get drunk before they die, and how much star formation is affected by this mechanism? And you have here a slow downfall mechanism as opposed to what people usually call quenching, which I would say is just a rapid quenching. The word quenching, even though I'm not an English native, for me is the mechanism that is violent and rapid. We usually call passive galaxies quenched galaxies. I think it's an error. We should call them passive galaxies. And then some of them are quenched, Some maybe just dying slowly, get drowned before, maybe they die by sickness, some are killed. We have to be able to disentangle all these mechanisms. So here I'm just going to disentangle these two and try to understand if the galaxies had been on the main sequence and if there was no slow downfall, I would have had more star formation in those galaxies than what I have. So I can compute the amount of star formation that I'm missing because of the slow downfall, and I can compare it to the amount of star formation that I'm losing by the fact that I'm building the red population. And if I assume that all the red population is built by the rapid quenching, I can calculate the rate at which this is done, and I can compare the two. And when I do that, as a function of redshift, I find that the fast quenching dominates above redshift 1.5 or 1.2, but then around redshift 1 to 0, there is nearly equivalently the same amount of star formation that is lost by the slow downfall as compared to what is lost by the quenching of the galaxies. So this is a mechanism that has to be taken into account. Now, there is another drop of star formation, of course, in galaxies in the main sequence. It's not only this break, but it's the overall drop of the main sequence with cosmic time. So we know, and we saw that in presentations of Reinhard and Linda, that the main cause of this drop is the fact that is the gas fraction, of course, of galaxies. And I won't go back again to the same figures you just saw, but I will try to address another signature, which is the geometry of the star formation within the galaxies that can be probed by ALMA to try to understand whether we see a change of the star formation rate distribution, the projected star formation rate distribution in galaxies as a function of specific star formation rate and cosmic time. So at redshift 0, you have here the projected surface density of infrared luminosity, which if you measure by 1.7 10 to the minus 10, using the Kelly-Cut relation, gives you the projected star formation rate density, because most of the star formation at these high star formation rates is dominated by infrared, and you can also use the UV. I will mention that later on. And this is the specific star formation rate of galaxies above the one you have in the main sequence. So this index here is what I would call the starburstiness of galaxies. So if you look at the main sequence here, SFR M star, the blue point is on the main sequence. It has a starburstiness of 1. And if you are above 3 times the median here, the main sequence, I would say it has a starburstiness of 3 and 10. So instead of saying starbursts are all those galaxies above a given ratio, you can have an intensity of the starburstiness in some sense, and you can see that galaxies are more and more compact in the local universe when they are more starbursty. Here the compactness is measured by radio imaging and also by the Spitzer mid-infrared imaging. Let me remind you also the very nice work by Guillermo and an interpretation by Avishai of the red and blue nuggets, where at a given specific star formation rate, galaxies with high projected surface density in the optical can be classified as blue nuggets when the sigma 1.5 is greater than, so it's a stellar mass over Re to the 1.5 greater than 10 to the 10.3, and the red nuggets when the galaxies are quiescent. So I'm mentioning that to you now because I will try to address what is the nature of the spatial distribution of star formation in those galaxies as seen with ALMA. So we have 2 programs here that I'm mentioning, one in cycle 1, one in cycle 2. Cycle 1 addressing the spatial distribution of star formation in redshift 2 ULURCs with a resolution that is, in fact, depending on the signal to noise ratio, but for the average galaxy we have here, we reach a precision of 0.15 kiloparsec resolution in those galaxies of masses between 310 to the 10 and 310 to the 11 at 870 microns observed. So in the rest frame, you divide that by 3. So 200 and something microns, so very close to the peak of the star formation rate density. And we have a cycle 2 set of galaxies at redshift 4, where we have targeted 113 galaxies in the 3 candles fields of good star, 3DS, and Cosmos that could be seen by the ALMA, and with stellar masses greater than 510 to the 10. And for 11 of them, we have resolved maps at 0.9 kiloparsec precision. Now, the galaxies that we have studied at redshift 2, if you compare them in the diagram of Guillermo, are exactly located in the compact blue nugget regime. Now, the question we want to address is whether they are also compact in star formation or the star formation is more diffuse, and what is the cause of the enhanced star formation rate in the high redshift galaxies. So here you have the HST images and the ALMA images of those galaxies, which are well resolved. The contours here are showing where you have 50, 68, and 90% of the 870 micron flux. And we use this area to measure sigma IR, which is the projected density of infrared luminosity. So if I go back to the figure I showed you before at redshift 0 between the starburstiness and projected infrared luminosity density, you can see this rise. And now if I look at redshift 2, here are my galaxies. And redshift 4, the galaxies are here. And you see that, of course, I am putting here a line as if I was fitting the points just to show you the range of evolution. There is a dispersion here of the redshift 4 galaxies, but clearly you see they are all pushed to higher projected surface densities in the infrared luminosity. And in practice, the sigma IR rises by a factor 1 z to the 2.5, which is much larger than the 1 plus z cosmological evolution you would expect. We did the same exercise with the UV sizes of the galaxies, and if you do the UV sizes, you see it's evolving only with the 1 plus z. So galaxies are getting more compact, have a much higher projected surface density of star formation in the infrared than in the UV, and that's normal because if you rise the compactness of star formation, you also rise the attenuation, and that is not followed up by the UV. So you're completely missing that with the UV, which is also the reason why you're missing the starburst with the UV, because you can correct the main sequence galaxy for the attenuation using the beta slope, but as soon as you're out of the main sequence, you do not see that. Perfect. And that, I think, is connected to this reasoning that you can see here. You have the main sequence as a function of redshift. You can draw a line above which any star formed in galaxies above that line, so above redshift 1.5, will have alpha element over iron ratios enhanced as the stars you see in present-day bulges. In other words, even though you can make stars in relatively rotating galaxies with, as Reinhard showed, relatively also large velocity dispersions, those stars are completely consistent with building the bulges of galaxies, even though they may be rotating when you see them. And so you don't need to have a starburst to build the stars of an elliptical of a bulge. Main sequence galaxies will end up in bulges, and as you can see here, they are forming stars in a very compact way. Just to give you an insight on the main sequence at redshift 4, it's very preliminary here. This is the stacked value of Herschel, and those are the detections. And although we cannot say, oh, this is a tight relation, we see that there is a relatively good agreement between the two. We still need to understand why you have many upper limits of galaxies we don't detect. Probably a large fraction of them are resolved, and that's why we are missing some flux. The large fraction of the time we obtained was done at too high resolution with ALMA. Now, the last point I would like to mention is these galaxies that are very compact at redshift 4, can they be, in some sense, the progenitors of the redshift 2 compact or little galaxies, and how do we find them? So this is an edge dropout. This is a galaxy that is not seen at 1.6 micron, but it's seen at 2 micron, 4.5, and 8 micron. And we have done a study with Tao Wang of a systematic study of H minus 4.5 galaxies greater than 2.25, which is a selection criterion to find star-forming galaxies which are highly obscured at redshift 4. We have split these galaxies into high and low Z galaxies. It is a high H minus 4.5 range as a function of J minus H. We use the J minus H to split into redshift, and we use a color-color diagram similar to the UVJ to split between passive and star-forming galaxies. And when we stack the candidate highly obscured star-forming galaxy at redshift 4, the median is 4.4 in Z-FOT, we can see that the far infrared LCD looks very similar to what you would expect for a galaxy at that redshift. Put on the SSFR versus redshift, these galaxies are located here, so prolongating the relatively mild rise that you see from redshift 2 to 4. So there is no clear plateau, but the main point I would like to stress here is twofold. The first one is a comparison of the number density or fraction of LBG selected galaxies with those galaxies. Above a mass of 10 to the 10.5, you see 5 times more galaxies selected with this technique as opposed to the LBG selection criterion. So if you were to measure the cosmic star formation rate density of galaxies at high masses, above 10 to the 10.5, you will miss a number of objects which is typically 5 times larger if you only use LBGs, and in terms of contribution to the cosmic star formation rate density, it's even more. Now, if you look at the effective radius of those galaxies, it is very similar to the one of the redshift 2 compact early type galaxies. And the number density of those galaxies is also very similar. I didn't give the number actually in this slide, but yes, they are here. It's 2.6 10 to the minus 5 per cubic megaparsec, as compared to 2 10 to the minus 5 per cubic megaparsec at redshift 2. So we think they are an extension of the objects that are seen at redshift 2 and 3 by Guillermo to redshift 4. So this is my conclusions. Actually, I want just to show you a very short snapshot on this image here. We just received the reply from the ALMA TAC, and we have a good ALMA survey that has been accepted of 22 hours to cover the full deep Candles region of the Good South field. So very soon we will have the full blind survey of Good South coming out of ALMA. We are ranked in the 10% at this cycle 3. Thank you. Yeah. I'd like to leave the question mark. So maybe we can discuss about that, because we did a full simulation with all varieties of n values that was in the simulation. That's what we used to try to estimate the uncertainty on the decomposition. But we can check if it's an agreement.
So the barrel objects, the compact star-forming objects that have compact star-forming cores from your data, what do you think is quenching them rapidly? The star formation? Because the idea is that those will soon be quenched and then become the compact quiescent. Any ideas?
That's a very good question. I would think that indeed at this compactness I would expect the star formation alone to be able to quench them. But this is just, I have no demonstration of that. But I would expect that, yes.
So I can't resist asking a question that's also connected to Piero's expertise. So on one of your last plots, you showed the cosmic star formation rate, the Maddow plot, and it looked like you're saying that these H versus IRAC detected galaxies make a substantial increase in the total star formation rate at these high redshifts.
Yes.
And the question is this going to put us back into a problem with the growth of the total stellar mass? The latest review by Piero and Mark Dickinson says that's now a solved problem. Everything is now consistent. Yeah. This is looking like it might make it inconsistent.
I think it's very consistent with what they wrote in practice. The reason why I'm looking at 10 to the 10.5 here is because the effect is strong here at high masses, and because they are metal-rich. You need metal-rich, highly heavy element rich and dust-rich galaxies to have these dust obscurations. Now, if you integrate the full cosmic star formation rate density redshift 4, the change you have with that is minor.
So even though it's a lot more than the ones
you detect with Lyman
at
high masses.
Last question, David.
I'm a little bit puzzled by your conclusion about the sigma IR, given that you have those non-detections, because if you include those, then I would assume that the set of points would in fact spread across your diagram, and any relationship that you're going to try to conclude would have to depend upon that sample. Am I wrong?
So it's...
that's a strong selection effect is what I'm trying to say.
You're right. And also, well, let's say we could not measure sizes of the low C19 ratio galaxies, and indeed you could have more extended galaxies at redshift 4 that could be shifting the thing if we were detecting them. It's a good point.
Few, it's okay, but
yeah.
you have piles of them.
Yeah. At redshift 2 at least.
Data anyway.
Yeah, and at redshift 2, all the ones we measured are compact, but indeed the ones we measured are biased. So.
Okay, thank you, David.
Thanks.